The problem statement from GATE Physics 2010 reads as follows. The figure shows a constant current source charging a capacitor that is initially uncharged. If the switch is closed at t equal to 0, which one of the following plots depicts correctly the output voltage of the circuit as a function of time? So the question says that we are closing the switch at t equal to 0 and we are required to plot this V out as a function of time. The switch is closed at t equal to 0. So this is a multiple choice question with only one correct answer and we are required to find the correct option. But first let's have a quick look at the current sources. On the left you have an ideal current source. So let's assume that this current is being supplied to a load. In this case I'm assuming a resistive load. So what's going to happen is that all the current that is being supplied by this, by the way, the current source is sitting in this rectangular box. We only get to see these two nodes, the top one and the bottom one, so we don't see what's happening inside. So if it's an ideal current source, it will have an infinite shunt resistance. What's going to happen essentially is that means all the current that is is that's flowing here will come out. So this means, so let's say if I measure the voltage here, so V out here would be is times RL, where RL is a constant load resistor, right? And let's try to evaluate let's try to apply a same load resistance of the same value over here. Let's try to see what is the output voltage in this case. Okay, so again is being supplied over here, right? And if you notice carefully, some of the current will flow here. Let's call this IP, right? And only IL will flow here. You can, if I apply KCL at this node, at the node over here, so I can write incoming current, which is IS, equal to outgoing current, which is IP plus IL. So IL would be IS minus IP, and correspondingly V out will come out to be IL times RL, which will going to be IS RL minus IP times RL. Now you can clearly see the output voltage here was ISRL. The output voltage in the practical current source is lower by a specific amount. So what effectively this means is that there will be somewhat lower power delivered. Lower power delivered over here, because some current is flowing inside the circuitry itself of the current source. So this is a practical current source, by the way. So so usually RP should be very high for a good current source, even a practical current source. So that's a key difference between these two sources. But for our problem, we'll assume that our current source is ideal and it's a constant current source, so it will provide us only a capital I current. And so we are closing the switch at t equal to 0, and we are also given that Q at t equal to 0 is equal to 0. The capacitor was uncharged earlier. Okay, and we know this famous expression Q equal to CV. So if I try to differentiate with respect to time on both sides, it will be dq over dt equal to d of CV over dt. We'll assume the capacitance does not change with time, so it will be C dV over dt. Okay, and so dq over dt is nothing but the rate of change of charge on the capacitor, which can be denoted by I in this case. So, and note, I is a constant, right? C is also a constant. So I'll rearrange the terms. It will be dV equal to I over C dt, right? Where V is the voltage across the capacitor. So what is the voltage across the capacitor? It's V out minus 0. So I can say dV out minus 0 is equal to I over C dt. So this will become dV out equal to I over C dt. Now we note that at Q at t equal to 0 was 0. So if I write this as CV out at t equal to 0 is also 0. Capacitance is not 0. So V out at t equal to 0 was equal to 0. Okay. So if I try to integrate it from time 0 to some random time t, and at time t equal to 0, V out was 0. So 0 to some voltage V out. So I'll get V out minus 0 equal to I over C t minus 0. Note I and C were constants, hence they could stay out of the integration. So this will give me V out equal to I over C times t. So what we got was V out equal to I over C times T. I is a constant, C is a constant, and let's say I'm putting V out at y-axis, so I'll take y equal to, I'll take this constant to be m, and time is the x-axis, so y equal to mx. So our answer should mimic y equal to mx. So if I see the four options, this is the closest option, right? But if that were correct, it would have been extended like this to infinity. That's not the case here. It's saturating at some specific, let's call this voltage V threshold, VTH. Okay, so there is some threshold above which the output voltage saturates. This is happening because in real life scenario, there is always a voltage rating. Let's say if you increase too much voltage across capacitor, this capacitor may blow up or this efficiency will go down. Similarly, these current sources are usually made up of BJTs, right, or FETs. BJT is bipolar junction transistors, FETs is field effect transistors. So usually current sources are designed out of these electronic devices, and they also have a maximum voltage, let's say VCC in case of a BJT, or VDD if you are using an FET. So there is a limit, there's an upper limit to the voltages which can be sustained. Hence at some specific voltage, we don't know what voltage, but the output voltage must saturate, and hence rather than going in to infinite output voltage, it will saturate at some voltage. That voltage we can't comment on. So D is the correct option. Thank you for listening.